For this problem, we're looking at a truss made up of members KB and CB. The loading on it is the vertical force there at node B. In addition to that, the temperature of members 1 and 2 are both increased by the same amount there of delta T. There's also the connection there over on the right-hand side. Joint B is connected to a roller, and the roller is to roll along this smooth vertical wall. What we want to do is find out, as a result of the thermal loads and of the mechanical load, what is the vertical displacement there of joint B, and what are the normal stresses in members 1 and 2. Before we begin, what I want to do is define a couple of things that we're going to need. One, we can see here that the length of member 1 is just L. We see that if we look at the length of 2, what we know here is that L is equal to L2 times cosine of 60 degrees. This here is 60. So therefore L2 is going to be equal to the length there of member 1L divided by cosine of 60. Also, in anticipation that we're going to be using the elongation displacement equation for trusses, we're going to define our angles of theta 1 and theta 2 for the two members of that truss. So theta 1, as always, you draw a line in the x direction, x given here. We measure at the base of the member in the counterclockwise sense, and we see that the member 1 is at theta 1 equal to a 0. And we also see here that the member 2, if we measure that from the positive x-axis in the counterclockwise sense, then that theta 2 is given by 60 degrees. I'm also going to call this angle phi, so I don't have to write down 60 degrees. Okay, so the problem here is laid out for us in terms of 4 different steps, so we're going to follow those. We begin with our equilibrium, and we're going to look at joint B. So at joint B, we have member force of F1 pointing to the left. We have member force F2 at the angle of phi, such as that. We have the applied force P, and the wall is going to be exerting a force of Bx on pin B. So in looking at joint B, when we sum forces acting on that in x, we're going to have minus F1, we're going to have minus Bx, we're going to have minus F2 times cosine of phi, and that for equilibrium is a 0. So that's our first equation. Second equation comes from summing forces in the y direction, and so there we have minus F2 sine phi. We have a minus P, and for equilibrium that sum is a 0. So that's equation 2. So those are what we're going to be using for equilibrium, and we see that it's not a good situation. The problem is statically indeterminate. And the reason for this is we have 2 equations, and in those 2 equations we have 3 unknowns. And those 3 unknowns are F1, F2, and the reaction force there of Bx. We need to come up with at least one more additional equation. But in the problems we have seen before, we know that those are going to come from our elongation and our compatibility equations. So as I write down E1 and E2, these are the elongation equations for members 1 and 2. We have F1 L1 divided by E times A. it looks like our E values are the same for all the members as well as the A's. So F2 then is F2L2 divided by EA. That's the mechanical part. The temperature part is going to be alpha delta T for both of these. They're both changed by the same temperature delta T. They have the same coefficient of thermal expansion there of alpha. So that gives us equations 3 and 4. And we know that what that's done for us is given us additional 2 more unknowns. So the scorecard shows that we have 4 equations now and 5 unknowns. No net change. But now let's look at our compatibility equations. So we will write down our truss equations. Let's say E1 and E2. E1 is going to be the horizontal displacement there at B times cosine of theta 1 plus the vertical component of displacement at B sine theta 1. UB times cosine of theta 2. VB times sine of theta 2. This gives us an additional 2 equations of 5 and 6, but it gives us also additional equations, or additional unknowns, I should say. There are VB and UB. But we have one more thing we need to say, and that is that the horizontal component of displacement of B is a 0. And that's because there's a wall. There's a wall that's preventing B from moving in the x direction as you load this up with the thermal loads and the mechanical load there of P. So we finally have, in order to solve, we have the right number of equations. We have 7 equations, and we have 7 unknowns. Let's write down what those unknowns are. The load carried by members 1 and 2. Recall we had the Bx, the reaction at B, as an unknown. We have the elongation of 1, the elongation of 2. We have the displacement UB, displacement of VB. So those are the 7 unknowns. So what we would do probably is start out here with UB equal to a 0. And what we get from here is the relationship that exists between the elongation of 1 and the vertical displacement of B, and also the relationship between the elongation of 2 and the vertical displacement. So quickly, we've gone here now from 7 unknowns to 6 unknowns with 6 equations, and you can solve those. So this problem here is not too much different than a number of the truss problems or truss problems with thermal loads we've seen before, except it's got one additional constraint, and that is there on the right hand side we're putting that wall along which B must move. That introduced for us an additional unknown Bx, but by enforcing the wall condition we have an additional equation. So we're right back with the right number of equations for the